Welcome back to Basic Electronics. In our discussion so far, we have considered the diode to be ideal when a reverse bias is applied. That is, we assume the diode to be off and the diode current to be zero. In this lecture, we will look at the effect of reverse breakdown of a diode on its IV curve. We will also consider an application where reverse conduction of a diode is beneficial. Okay, let us get started. Let us look at this region now where no diode is conducting, and in that case no current in this branch, no current in this branch, and therefore the current through R is 0. So therefore there is no voltage drop across R and VO is equal to VI. Alright, let us now look at the VO versus VI relationship for these two regions. So here is the plot. This region is VI greater than 1.7 volts. This is 2 volts, this is 1.7 volts. We have a straight line here with a slope equal to 1 by 4. In this region, when all diodes are off, we have VO equal to VI, that is a straight line with slope equal to 1 and passing through the origin. Note that this slope equal to 1 is not really looking like slope equal to 1 because these scales are different. Here we have minus 8 to 8 volts, and for the y-axis we have minus 4 to 4 volts. Okay, let us proceed now with the next situation, that is D2 conducting but D3 not yet conducting. And in that situation the current path is like this. Diodes D1 and D3 are not conducting and therefore they are shown in gray. Okay, now we have seen earlier that D2 just begins to conduct at VO equal to minus 2.7 volts. And what is the situation at this point? The current is just beginning to build up. So let us say it is still very small. So this voltage drop is small. This voltage drop is also small. And therefore VI would be equal to VO. So VI is also minus 2.7 volts. When we make VI more negative than minus 2.7 volts, that is VI less than minus 2.7 volts, we are talking about this region now. D2 is conducting and D3 is still not conducting. So what happens then is this current starts increasing as VI becomes more and more negative, and in that case VO is VI plus I times R. And what is I? This node is at minus 2 volts, this node is at VI. So the total voltage drop between these two is minus 2 minus VI, and from that we need to subtract the diode voltage drop, that is 0.7 volts. So therefore we have minus 2 minus 0.7 minus VI divided by R plus R2. So that gives this current I. So therefore we have VO equal to VI plus R times this current, that is VO equal to VI plus this is our I, that multiplied by R. This of course is a straight line, and the slope of this straight line is given by 1 minus R by R plus R2, like that, and that is R2 by R plus R2. R2 is 1K, R is 3K, so therefore the slope turns out to be 1 by 4. Okay, let us now look at the plot, that is VO versus VI in this region. We already looked at these two regions, this one and this one, and this is the new region now where D2 is on and D3 is still not on. So that is a straight line described by this equation here, and it has a slope of 1 by 4. Let us now talk about the final case, that is both D2 and D3 on, and let us first figure out at what point D3 just begins to conduct, that is this boundary here. So what is happening as we make VO more and more negative, that is make VI more and more negative, this current increases and therefore this voltage drop goes on increasing. At some point it becomes equal to 0.7 volts, and that is the point at which D3 turns on. So let us first find that point and then we will be able to complete this picture. When D3 starts conducting, we have two current paths, one through R2 and one through D3, like that. Now let us consider the case where D3 has just begun to conduct. That means this voltage is almost 0.7 volts but not quite. So this current is still 0 and this voltage drop is nearly equal to 0.7 volts. And in that case the current is like that, and we can use the expression that we derived for this current in the last slide, and that is given over here. So we have R2 times I equal to 0.7 volts, and we can solve this equation for VI. VI turns out to be minus 5.5 volts. What happens if we make VI smaller? That means more negative than minus 5.5 volts. All that happens is this current increases and the additional voltage drop appears across this resistance R. Okay. Let us now look at VO in this situation. That means D2 and D3 are both conducting. What is VO? VO is minus 2 volts minus 0.7 volts minus another 0.7 volts. So VO is then minus 3.4 volts. So in this region VO is constant, and that is equal to minus 3.4 volts. Here is the complete picture. In this region, that is VI greater than 1.7 volts, D1 is on. In this region, that is VI between minus 2.7 and 1.7 volts, no diode is conducting, and we have VO equal to VI. In this region, that is between minus 5.5 volts and minus 2.7 volts, D2 is on, D3 is not on, and finally in this region both D2 and D3 are on. And this is the region that we were just discussing. For VI less than minus 5.5 volts, VO is minus 3.4 volts and it is constant, that is minus 3.4 volts. Alright, the sequel file for this circuit is available and you can play with it. You can try to change the resistance values, for example, predict what should happen, and then run the simulation and check whether your prediction is correct. Let us now look at the IV curve of a real diode, and in particular we want to look at the reverse bias region, that means with applied voltage less than 0 volts. In the reverse direction, an ideal diode presents a large resistance for any applied voltage, ideally infinite resistance, and that is indeed what we have assumed so far in all our examples. This is the assumption that we have made. Now that is not quite true about a real diode. A real diode cannot withstand indefinitely large reverse voltages and breaks down at a certain voltage called the breakdown voltage. In the example shown over here, this diode is seen to break down at about minus 5 volts. Now this breakdown voltage VBR is usually treated as a positive number. For this specific device, VBR would be 5 volts. and the applied voltage would be minus 5 volts. Alright. When the reverse bias VR is greater than VBR, that is when the applied voltage is less than minus VBR, in this case minus 5 volts, the diode allows a large amount of current as seen over here. And if this current is not constrained by the external circuit, then chances are that the diode would get damaged, because this V times I would be too large. That is the power absorbed by the diode, which has to be dissipated as heat. And if that heat is not dissipated effectively, the diode temperature will rise and eventually the diode would get damaged. Let us make a few comments on the reverse breakdown. A wide variety of diodes is available with the breakdown voltage ranging from a few volts, as in this case, to a few thousand volts. That's a very large breakdown voltage. And generally, higher the breakdown voltage, higher is the cost, because if we want to make a diode with a breakdown voltage of 1000 volts, for example, the manufacturing process that it requires is very stringent, and that adds to the cost. Diodes with high breakdown voltage are generally used in power electronics applications and are therefore also designed to carry a large forward current. How large? It could be tens of amperes or even hundreds of amperes. And when a diode carries a large current of that kind, it generates heat which must be effectively dissipated, and that is why these high power diodes look very different than diodes that we use in electronics labs. Let us look at some images. Here are some low power diodes that one would use in an electronics lab. The scale is centimeters, so this is 1 centimeter. So we see that they are fairly small. And here is a high power diode. Notice that this cable is much thicker because it has to carry a large current. And notice also this heat sink, which has to dissipate the large amount of heat that is generated by the diode. Now typically circuits are designed so that the reverse bias across any diode is less than the breakdown voltage rating for that diode. And in the examples that we have seen so far of diode circuits, this has been the case. So therefore we did not worry about a diode breaking down in those examples. However, there are diodes which are supposed to operate in this breakdown region, and those are called Zener diodes. So Zener diodes typically have VBR of a few volts, and that is denoted by VZ. And these Zener diodes are often used to limit the voltage swing in electronic circuits. A little later we will see an example of an electronic circuit which does exactly that. Alright, here is the symbol for a Zener diode. It looks very much like the ordinary diode, except it has these little line segments over here. Let us look at this commonly used configuration with two Zener diodes connected back to back. That is, the N of this D1 is connected to the N of D2. So they are pointing in opposite directions. And we want to know what I is, the current here, as a function of the total voltage drop V shown here. And we will assume that for each of D1 and D2, we have the IV relationship shown in this graph. So this could be I1 versus V1, I1 versus V1, or it could be I2 versus V2. Remember, I2 has to point the other way from P to N of D2, and V2 also has the opposite polarity as compared to D1. So we assume that in the forward direction, the diode starts conducting at V equal to V on, and it has 0 on resistance. And then in between, that is between V on and minus Vz, the diode passes no current, the current is 0, and it breaks down at V equal to minus Vz. And we will assume this breakdown to be sharp, and that this resistance, when the diode does conduct in the reverse direction, is again 0. So 0 resistance, infinite resistance, and 0 resistance again. Let us consider the case in which I is positive, let's say 1 milliamp. So 1 milliamp is flowing from this node to this node. And how is that possible? It is possible only if this diode conducts in the forward direction and this diode conducts in the reverse direction. So for this diode, we have a current, a forward current of 1 milliamp. Let's say 1 milliamp is somewhere here, and we are on that curve, I1 versus V1. For D2, the reverse current is 1 milliamp, and so therefore we are somewhere here. And so therefore it has a voltage drop of minus Vz across it. And let us see what the complete picture looks like. So D1 in forward conduction, D2 in reverse conduction. V1 is V on, V2 is minus Vz. And our interest, of course, is what is this total voltage drop. So the total voltage drop is V1 minus V2, and that is V on minus Vz. So that turns out to be V on plus Vz. Let's take an example. If V on is 0.7 volts and Vz is 5 volts, that is this minus Vz is minus 5 volts, then the total voltage drop V would be 5.7 volts. And the other situation is completely analogous. Let's now consider I less than 0, and in that case the current goes in that direction. D2 is now under forward bias and D1 is under reverse breakdown. And V2, this voltage, is therefore V on, and V1 is minus Vz. And now once again we can find the total voltage drop. What is the total voltage drop? Is V1 minus V2 as before. V1 is minus Vz, V2 is V on. So V1 minus V2 is minus Vz minus V on, or minus Vz plus V on in brackets. So that for our example here turns out to be minus 5.7 volts. And for any voltage between these two limits, that is 5.7 and minus 5.7 volts, no conduction is possible, and therefore the current is 0. So putting all of this together, we get the I versus V relationship for this entire combination as follows. So that is I, that is V, no current between these two limits, and at V equal to Vz plus V on, the combination starts conducting in the forward direction. For V equal to minus Vz plus V on, it starts conducting in the negative direction. Here is a circuit in which the Zener diode pair that we saw in the last slide has been used. This is the input voltage, that is the output voltage, and we want to plot VO as a function of VI, and then we will figure out what function this circuit is performing. Let us take V on equal to 0.7 volts for each of these diodes. That means when they conduct in the forward direction, the voltage drop across the diode is 0.7 volts, and let Vz be 5 volts. That means if the diode conducts in the reverse direction, then the voltage drop across the diode is minus 5 volts. And as we saw in the last slide, here is the I versus V relationship for this diode pair. The current I is on this y-axis here, and the voltage across the diode pair in this case is VO. So VO is on the x-axis. Now if the diode combination conducts in the forward direction, that means if the current is positive, then we know that the voltage across the diode pair, that is VO, must be equal to Vz plus V on. In this case 5 plus 0.7, that is 5.7 volts. And when the diode combination conducts in the reverse direction, that means when the current is going like that, then VO would be minus 5.7 volts. What is the condition on Vi for the diode pair to conduct in that direction? In that situation, VO would be 5.7 volts, and this voltage drop would be positive because the current is going like that, and therefore Vi would be 5.7 volts plus this voltage drop, and therefore clearly Vi must be greater than 5.7 volts. Let us now consider the other situation in which the diode pair is conducting in that direction, and when that happens, we know that VO would be minus 5.7 volts. For convenience, let us take this node as the reference node. So we have 0 volts here. With respect to that reference node, this node is at minus 5.7 volts, and the current is going in that direction. This node is at Vi. So the voltage here is equal to VO minus this voltage drop, and that is clearly less than minus 5.7 volts. To summarize, we need an input voltage greater than 5.7 volts for the diode pair to conduct in that direction, and we need an input voltage less than minus 5.7 volts for the diode pair to conduct in the opposite direction. Let us now put all these observations together and plot VO as a function of Vi. Here is the plot of VO versus Vi, and let us make sure now that the features in this plot are consistent with our observations. For Vi between minus 5.7 volts and plus 5.7 volts, no conduction is possible, as we argued earlier. If no conduction is possible, there is no voltage drop across this resistance, and therefore VO is equal to Vi. And this equation represents a straight line with a slope equal to 1, and it passes through the origin like that. Okay. Point number 2, for Vi greater than 5.7 volts, D1 is forward biased, D2 is reverse biased. The current flows like that, and the output voltage is V on plus Vz, that is 5.7 volts, as shown over here, and of course it is constant. The excess voltage, that is the difference between Vi and the output voltage, that is V on plus Vz, drops across R. As an example, let us say Vi is 10 volts. Of this 10 volts, 5.7 volts will drop here, and 4.3 volts will drop across R. And similarly, for Vi less than minus 5.7 volts, D2 is forward biased, D1 is reverse biased, that is it's under reverse breakdown. The current flows like that, and VO in this case is minus Vz plus V on, that is minus 5.7 volts, and that is shown in this part of the graph. Once again, the excess voltage, that is the difference between Vi and minus 5.7 drops across R. So we observe that as long as Vi is in this range, that is from minus 5.7 volts to plus 5.7 volts, Vo is equal to Vi. But if Vi exceeds 5.7 volts, then Vo gets limited to 5.7 volts. And similarly, if Vi becomes less than minus 5.7 volts, Vo gets limited to minus 5.7 volts. So this circuit serves to limit the output voltage. On the positive side, the limit is 5.7 volts, and on the negative side it is minus 5.7 volts. And that is why it is called voltage limiter. Alright. One question that we now want to address is how to choose this resistance value. Here we have 1K. Could that be 10K or 10 ohms? How do we go about selecting this value? Now notice that if we are in this region, if Vi is between minus 5.7 and plus 5.7, then this diode pair does not conduct. There is no current through this resistance, and in that case it doesn't really matter whether it is 1K or 10K or whatever. But when Vi exceeds 5.7 volts, for example if Vi is 10 volts, then there is a current through R. Now out of this 10 volts, 5.7 will drop here, 4.3 will drop here. So the current in this case would be 4.3 divided by 1K, that is 4.3 milliamps. Now if we make this 10 ohms for example, then the current would be 4.3 volts divided by 10 ohms. So that is 0.43 amperes, and that's a rather large current, and this voltage source may not be able to supply that current. So this current limiting functionality is what we need to consider when we select this resistance value. In conclusion, we looked at how reverse breakdown of a diode changes its IV relationship. We studied the IV curve for a pair of Zener diodes connected back to back. We also looked at an application based on this back-to-back pair. We will now move on to some more diode applications in the next lecture. Until then, goodbye.